All right, an optimization that is impossible in Rust. So we're going to read this, and then we'll go back and we'll read this one because I'm actually curious about that. An optimization that's impossible in Rust. We don't have enough string types in Rust? Okay. Oh, don't we have enough? Oh, gosh. Yeah, I do have severe dyslexia. Yay. It's your guys' fault. You listen to a guy who can't read. Okay, that's not my fault. Last time I checked, I looked at my watch. I didn't make this decision. You did. As I'm studying database systems for my master's degree in Germany, this article, Why German Strings Are Everywhere, immediately caught my attention. I was pretty excited to learn it's the string data structure described in a paper, Umbra, a disk-based system with in-memory performance. Interesting, okay. Which had been introduced to me through another paper about its storage engine, LeanStore, in-memory data management beyond main memory. I was even more interested to learn that it's been implemented in many different data solutions like DuckDB, Apache Arrow, and Polars. Is Polars the Pandas replacement, right? Prime getting old? No. Victim blaming much? It's your guys. You're the victims. Actually, I feel like you're actually the benefactors. You know, the more I think about this, the more I think you're actually the benefactors of my inability to read than anything else. No. Polars is the data frame lib in Rust, but Polars is also a Python library. Pola.rs is the Rust one. He's on to us. One thing that particularly stood out from the article had me puzzled was the following claim. This string implementation allows for the very important short string optimization. A short enough string can be stored in place, i.e., we set a specific bit in the capacity field, and the remainder of the capacity, as well as the size and pointer, become the string itself. This way, we save on allocating a buffer and a pointer dereference each time we access the string. An optimization that's impossible in Rust, by the way. Winky face. That's super cool. Okay, so before I look at any of the details, any of that, I'm having a hard time thinking about that because the first thing I'm thinking about is that I thought a string was pointer, len, cap, right? And so therefore, it's a super fat byte, right? It's a super fat pointer, triple fat pointer. And so does that mean it stores a bit right here? And so what happens? So if I get this correctly, the pointer points off to a memory space like that, right? And so therefore, instead, a short string optimization is that this memory space is actually just stored right here. That's pretty nifty. Okay, no cap for real on the stack. On God, man. Damn. If I correctly interpret the statement, it's objectively wrong because there are already lots of packages in Rust that support this exact feature, e.g. CompactStir, SmartStir, and SmallStir. Moreover, Polars, an example from the article, is written in Rust and implements Umbra-styled string. I got nerd-sniped and started implementing German string to show myself it was possible. I can't blame the guy for getting nerd-sniped because literally this right here is me getting nerd-sniped.
So rather than letting the AI fail and requiring the human to always give it feedback until the final result is correct, in some cases you can automate the feedback process and run the AI on a loop. So in cases where you can automatically check for...
So I built my own. I built my own that looks like this. Run generated code, run test, or run code gen, run test, run reasoning. And it just does it in a loop. That literal one line got me to build an entire AI thing because I couldn't help it. I was just like, I gotta figure this out. Okay, we're gonna prompt the AI, we're gonna run the test, and then we're gonna get the AI to reason why it's wrong. And oh my goodness. I get it. I totally get getting nerd sniped. It happens. It happens to the best of us. Don't feel bad. How much better was it? It was pretty fun. It was a fun learning experience. I learned a lot more about prompting. What's a nerd snipe? Someone suggests something and it's impossible to do X, or hey, this is really, really good if you do it this way, and you don't believe them, and then you do it, and then you end up writing it all. It's called getting nerd sniped. All of a sudden, you find yourself programming a whole bunch, right? You just can't help it. I just can't help it. All right, let's see. There's a certain type of brain that is easily disabled. If you show it in an interesting problem, it involuntarily drops everything else to work on it. Yep, it has led me to invent a new sport, nerd sniping. See that physicist crossing the road? Hey, on this infinite grid of ideal 1 ohm resistors, what's the equivalent resistance between the two marked nodes? Oh gosh, I don't even know what it is. Interesting. Maybe if you start with, no wait, you could, vroom. Oh, he's dead. I'll have no part in this. Come on, man. Come on, make a sign. It's fun. Physicists are 2-point mathematicians. 3. Oh, so he killed the guy. Oh, he killed him in the middle of the road. Okay, I get it. Nerd sniping. It's pretty funny. It's a pretty funny one. In this article, I've only heard nerd sniping. I didn't realize that it came from XKCD. Right? In this article, I'll describe how I implement German string and the challenges of doing so in Rust. Specifically, I'll examine how to enable shared ownership of such data structure. Providing unique ownership is relatively trivial, and there is already a nicely written tutorial from the Rustonomicon teaching you how to implement vect, which is not much different from a string. But first, let's talk about the concept of German string. Okay, don't we have enough string types in Rust? The term German-styled string was coined by Andy Pavlo in one of his lectures, Advanced Database Systems, German string. By the way, I got nerd sniped by this one, an optimization that's impossible in Rust. Look at this. I'm reading an article all because of the title. I'm in this photo and I do not like it. Yeah. In one of his lectures on Advanced Database Systems, German string, German-styled string, and Umbra-styled string all refer to the same concept. At a high level, strings are conceptually simple, just a sequence of characters. However, there's more going on with strings than one may realize. Even the concept of a character is already a complex thing itself, depending on the use case. How a string is represented in memory can differ widely. Just within Rust, there are several different types of string. Each of the following types has its own corresponding borrowed version. String, UTF-8 encoded, C string, and owned C-compatible null-terminated string with null bytes in the middle, with no null bytes in the middle. OSS string, an owned mutable platform native string that is, but is cheaply interconvertible with Rust strings. A thin wrapper around OSS string or operating system string representing an owned mutable path. Okay, yes, and there's a lot more type of stuff. The nice part about Zig, there's just an array of U8. Well, didn't Chris Latner say he was nerd sniped into creating LLVM? Yes. Yes, he did. Rust string. String is the most commonly used type in Rust, and thus will be the subject of our discussion. Internally, string is just a vec of U8, i.e. a sequence of bytes. Additionally, that sequence of bytes must be UTF-8 encoded, meaning a character is not always just a byte, but ranges between 1 and 4 bytes. The implementation of string is as follows, minus some details. Yeah, so so this is assuming string as the bytes have some sort of like displaying information to it, whereas Zig or other languages often will treat string as not UTF required, right? It's just simply, it is just a list of 8 bits, right? 8-bit chunks. And so that's how, of encoding. Yeah, there's an assumed encoding to string. It's just a vect8. Vec is just a raw vec length size. There we go. Raw vect equals this. Pointer, capacity, allocate. I'm not sure what this is. Global allocator. I don't know what's going on here. Public unique. I don't even know what we're looking at. I still don't know what phantom data is. I probably need to learn. I quit learning Rust when I got to phantom data. Honestly, I was just like, I'm tired of this. That looks too complicated, but essentially a string consists of 3 parts on the stack that take up 24 bytes. Length, capacity, pointer. Yep, length, capacity, pointer. Okay, so pointer's at the end, not at the beginning. Okay, whoopsie daisies. Phantom data is just there to make use of T. Is that it? But so does non-null. I don't know. As a string is mutable, and I think it has something else. I think there's something else, but I can't remember what it is. I read John talking about phantom data, and I think I got it for a little bit, but now I can't remember. It's been a while. Anyways, a string is mutable and can be appended to when needed. So we need to track the length and the capacity with an invariant that cap is greater than or equal to length. Whenever length grows larger than cap, a new buffer is created with enough capacity to hold the string with a new length, and the old buffer gets deallocated. German strings. Theoretically, a string can hold infinitely many different kinds of text within infinite sizes. Nonetheless, the real-world usages of strings, especially in databases, can observe a few common characteristics. Most strings are short. Most strings don't change. Only a tiny substring is looked at when comparing or ordering strings. Okay. Based on those observations, German strings was invented to address these specific use cases, aiming to accelerate string processing performance. The basic idea follows what is called short string optimization. Instead of allocating a buffer on the heap, we can avoid the expensive allocation and store the bytes directly on the stack for short enough strings by repurposing cap and pointer. Having no allocation also means we don't need to follow pointers when accessing short strings. This is actually such a cool optimization. This is super cool. This is super, super cool. Internally, a German string takes only 16 bytes on the stack and has two different representations depending on the string length. A German string is also immutable by removing the need to track the buffer and capacity. Okay, so you got 4 bytes here, 12 bytes on this thing. Okay, cool. This is super cool. Oh, is it just like small vec? Is small vec also this exact same thing? Okay. Awesome. German string layout for short strings. Strings at most 12 bytes are inlined and stored directly on the stack. Out of the 16 bytes, 4 are used to hold the string length and 12 are used to hold the string content. Nice. Long strings. Okay. Strings over 12 bytes are heap allocated like string and have a pointer to the heap allocated buffer, but there are a few twists. Only 4 bytes to hold the string length instead of 8, thus limiting the string sizes to 4 gigabytes, which is completely acceptable. This is acceptable because most strings used in the real world are short. Yeah, they're never... Yeah, it'd be super unusual to see something of that size. A 4-byte prefix from the string is inlined and stored directly on the stack. For most string comparison operations, this can help avoid expensive pointer dereferencing when the result can be determined just using just the prefix. Oh, nice. Okay. Oh, that's super clever. Just the first 4 bytes? Oh, that's super, super clever. Okay. Yeah, because you're just doing this initial check, and if these two things don't equal, then there's no need to actually check the full length. Oh, that's like super duper clever. People be so dang clever. 4 gigabytes is not enough for German words? Yeah, so German of you. Or German strings, or G strings for short. Damn, I don't know how I didn't see that coming. Dude, I didn't know programmers would be busted out here. It's crazy. Now that we know the basic shape of German string and its motivation, let's see how we can implement it using Rust. To start, we aimed to implement an owned immutable string that is UTF-8 encoded and supports the optimization techniques described earlier. Moreover, the heap allocated buffer will have shared ownership using atomic reference counting, allowing us to reuse it across threads. Interesting. Atomic reference counting on your strings. That may not be wanted. I mean, you may want RCs as well, you know, maybe being able to specify. I always feel like whenever I use arcs and RCs, I kind of feel like I'm kind of like ruining the use of Rust. I always feel just bad using them, you know, because it's just like now you're no longer maintaining the lifetime and the ownership and saying, hey, it's this long and that's it. It feels dirty, but it's fire. Yeah, it is. I feel dirty too. Yeah, whenever I use it, something in the back of my head whispers, hey, man, come on. What are you trying to do? What is this? You trying to do Objective-C over here? It really is okay. I know it's okay. But I still feel it. I still feel the Objective-C calling to me. Struct Umbra string, length 32, data this. Okay. Union, data. I didn't realize they had unions. Oh, did I not know that? I didn't know that. I didn't realize that. I thought they just had enums. A buffer of 12 and a pointer manually dropped shared dyne bytes. Okay. Struct shared dyne bytes, prefix of this, pointer, non-null, non-null shared bind bytes, phantom, shared dyne bytes inner. Okay. Using Rust layout rules, shared dyne bytes has a size of 16 bytes and an alignment of 8, resulting in an Umbra string having a size 24 bytes and an alignment of 8. This is different from the layout we want. To make Umbra 16 bytes, we can lower shared dyne bytes alignment to 4 and make everything correctly sized using the repr pact 4. However, Clippy, Rust linter, won't be happy with us when we reference the pointer field in shared dyne bytes because we might create a reference to an unaligned address, which is undefined behavior in Rust. While we never need to make such a reference, we are prevented from using some APIs on pointers, which are nice to have. Length, padding, prefix, padding, pointer. Okay, so that's not Umbra string layout for long strings with fields. Okay, but that's not right. That's not, look at that. That doesn't feel right. That's not right. Oh, move the chat up. Yeah. Sorry, I have the chat there so it doesn't intersect with alerts. Here, let me just grab alerts for a second, and I'll just move alerts over again. There you go. The Rust linter is called Clippy. Yes, it is. I also refuse to use the Rust linter because it has crappy opinions. I like the return keyword. Suck it, Rust. I don't care. A more considerable annoyance is that this complicates implementing string comparison and ordering. When comparing or ordering strings, we want to deal with prefix before anything else. With this layout, we must first check the string length to determine whether data is a buff or a pointer before getting to the prefix. To overcome that, we can mark everything with C repr or repr C and rely on the invariant that prefix is the first field in shared dyn bytes. As a result, we can interpret data as a buff without checking the length and still be sound if we only access the first 4 bytes. A better approach without relying on such invariant and freeing us from worrying about field orders is as follows. Okay, Umbra string has now length, prefix, struct. Okay, union is going to be either 8 or a manually dropped shared dyn bytes. Okay. Memory-wise, there's no difference compared to the repr C packed 4 version. Instead of having a 12-byte union, our new union trailing is only 8 bytes containing either the last 8 bytes of the string or a pointer to a heap allocated buffer. Here, the prefix is pulled out of the union for easy access, and Rust allows layout rules to work its magic without too much inference from us. Having the prefix as 4-byte array also improves performance because comparing fixed size arrays performs much better than comparing slices. Yeah. Okay. So I never knew that it had union. What are the? I wonder. I've never seen the semantics around using union. Can you still just match on a union and just say like if it's buff, it does buff. If it's pointer, if it's pointer. And if you can do that, how does it know if it's buff or if it's pointer? That's the one thing that I'm a bit confused on is how do you know which is which when it comes to this? Because it's not like a tagged union. You can't match. Yeah, I figured you could match because it doesn't have a tag. You have to check the bit that specifies the short string. Yes. Okay. So that means there is a bit somewhere that says the short string. Okay. So you're doing the manual understanding of the union. Okay. Super cool. I didn't realize you could do that with Rust. Hey, today I learned that Rust has unions. I always just thought it had enums. I didn't realize it had unions. Aren't they both valid simultaneously? They are technically both valid simultaneously. That is a union. I just didn't know that you could do that. Cool. Atomic reference counted bytes. Shared dyn bytes and atomic reference counted byte slice behaves like an arc. This begs the question, why don't just use arc U8? Dynamically sized types. Most types in Rust have a statically known size and alignment. Dynamic sized types, DSTs, are expected to come from this rule, and Rust exposes 2 major DSTs, trait objects, dyn traits, and slices. Because DSTs don't have a statically known size, they can't be on the stack and must be accessed through a pointer. Consequently, every pointer to a DST is a fat pointer consisting of the pointer itself and additional information about the data being pointed to. In this case of a slice in which we're interested, the extra information is length. The results in arc-T having a slice of 16 bytes instead of 8, causing Umbra Stream to take 24 bytes instead of 16. Okay, this makes perfect sense. I see why they don't do that. Okay. Do people understand this? The reason why this makes sense is that when you have a slice, you don't get to know how long it is. At compile time, you need to know what you're putting on, the stack versus the heap. And so this is unknown. So therefore, it has to have 2. That's why it has to have 2 sets. It has to have the pointer and then where the pointer plus the length, right? It has to be able to understand how to put it onto the stack. And so you can't just do something like this where you have either the data itself or a pointer to the data, which is then specified by this thing over here. The reason this is so hard, really, is because Rust doesn't deal with bit fields. So in C++, you can make this a lot easier with bit fields. Yeah. It's not an unknown. Yeah, exactly. Are we just edging memory layout? We are. This is actually super interesting. I'm loving this, by the way. Umbra string layout using arc U8. We know that Umbra string already keeps track of the length, and the extra length associated with the fat pointer can be discarded. Correct. That's why it's just a pointer, because you already have a length. We need a way to turn a fat pointer into a thin pointer, and that's not supported by arc-T. Currently, there's no way to construct a DST, and we can only create an instance of a custom DST by making it generic and performing unsizing coercion. Okay, I don't understand. I've never got this far into Rust, so I don't understand that. Having the problem described, here are our structs describing a reference counted bytes, slightly different from the previous example. Okay, so we repr C, shared dyn bytes. It's a pointer to non-null this. I don't get this generic. What is this generic doing? Is this generic saying it's an array of 0 bytes? I don't get that. And same with that one. Yep. I got too stupid for this one. I don't get it. Shared dyne bytes inner. Atomic U size. Okay, so this is for the atomic reference counting. It's a ZST, a zero sized. Yep, I'm not sure what they're doing here. Okay, so a lot of people don't understand. And then the data T. Okay. A struct can be made a DST by having its last field be a DST. Here, shared dyne bytes inner holds a reference count and a generic value over an unsized type. Shared dyne bytes inner is always allocated on the heap, and the atomic count tracks the number of references currently being given out. By allocating both the reference count and data, we can avoid one extra allocation and indirection. While it is generic, we are only interested in two specializations of the type that have the exact struct alignment and field. Okay, shared bytes dyne pointer, shared byte dyne pointer. These two, it has a count of 2. All right, shared bytes dyne, this one has a counter of 1. Okay, we get that. Shared byte dyne inner is a dynamically sized, and pointers to it are fat. This one is statically sized, and the pointers are thin. Oh, that's why they say that. Okay. So by having the let me get this straight. By having the type be a known size, there is no fat pointer. Is that what I'm saying? It's able to say, oh, this thing's actually a thin pointer. In other words, it can drop the length field because the length is already known on it. I think is that what I'm saying? That's wild. Okay, so you're well past my ability here. One cool trick we can do is converting between fat pointer type mute share. Okay, aren't we already in unsafe territory at this point? And a thin pointer of mute shared dyne bytes inner. This conversion allows us to add and remove information about slice length from a pointer depending on how we want to use it. Converting a fat pointer to a thin pointer is easy. Just a single cast. Bada-ba-bam. Okay. Fat pointer, thin pointer. Okay, but there's more dark magic to converting a thin pointer to a fat one. Instead of a direct cast, we must first turn a thin pointer to a slice with a specific length, which tells Rust to embed information about the length into the pointer. Only after that can the slice pointer be cast into a pointer to our custom DST. Thin pointer from here, fake slice, pointer, standard pointer slice from raw parts into this one, and then we do a fake slice as this one. Oh, okay, there we go. Allocating. Now that we can convert between a thin pointer and a fat pointer, we can start allocating memory for it. Unless we can coerce a statically sized type into a dynamically sized type, we can only create a value of a DST by manually allocating it. Before doing that, we must define a layout and allocate the value. We have a new layout, which extends this array layout of U8. Expect the layout to be this one. .0, it must be a tuple of some sort. Pad to align, layout. Boom, let's go. Let's go, .0. Let's go, .0. That still to this day, that always kind of weirds me out a little bit. Isn't a slice from raw parts mute unsafe? Yeah, you can tell it's unsafe because look, you can tell things are unsafe mode because you're right here. You don't use pointers in Rust. You use references. When you're in unsafe Rust, you'll see things like this. You're now in unsafe land, unless if I'm completely incorrect. So 0.0 is the equivalent? No, it's not the same. 0.0 means the first item in a tuple. So does the install wizard do the dark magic for me? Could the .0 have to do with it being a union? Ooh, it could be a union, but not the underlying struct. I assume whatever comes back from this thing right here, this layout is, I assume this is an option. It's something that you can call .expect on. So it's either an option or a result or whatever it is. So you can do that, unwrap it with an exception, or with a program halt panic, and then grab the first item out. It's a tuple of some sort. Unsafe, cursed shit, yeah. The layout is constructed by first creating a layout for shared dyne bytes inner, where the field data has size types. Taking no space, we then extend that layout with the layout of type byte array, resulting in a layout for shared dyne bytes inner with a slice of U8. With that layout, we can allocate just enough space for our atomic count and a byte array of arbitrary size. Ah, classic. Classic. We just got to do that. Honestly, Yo, dog, I'm happy for you, or I'm sorry. Fat shaming pointers, we are. This is basically C++. This is actually harder than C++. You've now officially made Rust more confusing than C++. Congratulations, or I'm sorry for you. Looks good to me, yeah. Ted was right. Ted was actually right. We take a lazy approach to allocation. Nothing is allocated if the given slice is empty. If it's not empty, we do the following. Allocate using the layout we defined, cast the returned pointer to a fat pointer to our DST, copy the data from the given slice into the data field, cast the fat pointer back to a thin pointer, and store it. Boom. That's what this one is. This is the fat to thin, right? Yep. A lot of copy, non-overlapping. Yeah, like I'm completely, at this point, I've lost the game with Rust, and I'm only vaguely following what's happening now, but I want to finish it because it's very difficult. Unsafe Rust sounds like C. It's a lot harder than C because you still have to do all the things. Let me leak code while I see you. Okay, do it, baby. Because our reference counted type doesn't have the information about the length of the array it holds, we can't implement drop for it. Instead, we provided a method for the user to type to manually deallocate it by giving the correct array length. Deallocate unchecked. All right, if length is greater than 0, let inner unsafe pointer. Okay, if it equals 1. Okay, so upon drop, so this inner count right here, so this would be the amount of atomic references. If that equals 1, then we need to drop it, right? Because that means you're the last one to drop it. Inner count load, atomic ordering acquire. Unsafe. Deallocate self pointer as cast U8. Okay, yep. I haven't done any of these things, so now I'm deep. Unsafe Rust is hard because it makes unsafe C safe. Yeah, that's fair. That's a fair way to say it. You don't do this stuff every day unless if it's specific to a C-lib project. Yeah, you don't do this stuff very often. But Rust also, I mean, this is a great, this is a great reminder for when Rust is hard, it's really, really hard. When called, the method first checks if the given length is non-zero. If it's 0, no memory was allocated, and we don't have to do anything. When the memory is allocated, we decrease that reference count and see if we're the only owner. If we are the only owner, we deallocate using the layout from earlier. Yep. Cloning. Similarly, we can't implement clone for our type and rely on the user-provided length to know if the memory was allocated. Cloning involves no copying, just incrementing a reference count. Yep. I don't know what a non-null dangling is. I don't know why we're dangling. Else, we get this thing, we add to the atomics, and then we do this. Then we get the pointer. Let pointer if length equals 0. There we go. Still, the phantom data. Slice. Slicing. Getting a slice to the underlying array also relies on user-provided length, and it is done in 2 steps. Casting the thin pointer to a fat pointer, creating a slice using a pointer to the data field, and the user-provided length. There you go. There's that fat pointer to thin, right? Or is this? No, that's not a fat pointer to thin. That's just a fat pointer, and then it's actually getting it, and it's returning it from right here. Or just doing a default length of nothing. Okay, so that's like the 0. That's the 0 length, and then this is the one that we're actually doing the unsafe operation over. Okay, wow. When I'm unable to sleep, I'll read this article. Yeah, putting things together. With all the essential components, we can now start implementing a German string. While much is needed to provide a usable string, we only present some basic functionalities. Allocating, creating a string is straightforward. We copy the prefix while handling 2 cases. If the string is almost 12 bytes, we inline the suffix. Otherwise, we allocate a new shared bytes dyne holding the string content. I'm sure anyone could understand this eventually, right? It just might take a bit of effort right here. So you got the bytes, you got the length. If it's over the largest size, it can't do that. We get the prefix with the prefix length. We get the trailing by slicing that stuff out. If it's less than inline length, then we don't need to do it. Then the trailing, obviously, we must do some sort of writing stuff. Else, we copy the slice from one side to another and create the trailing with the manually dropped pointer right here. Then we return this right here with the length, the prefix, and the trailing. And then allow Kippy cast possible truncation. Drop. Deallocation can now be provided by implementing drop for Umbra string because it has all the needed information. We'll see if there was any data to be deallocated by checking the length. If there's data on the heap, we deallocate the dealloc unchecked method introduced earlier. Drop. Function drop. Oh, weird. I didn't realize. Wait. Oh, yeah. Never mind. Sorry. So we're doing the trait implementation for drop. The function drop takes immutable self. We get the length. If the length is greater than the inline length, then we need to do this thing right here. Right, we need to drop it from right here. Okay, clone. Similarly, we can now implement clone from Umbra string. We copy the bytes to a new instance when the string is inlined. Otherwise, we copy the prefix and delegate the clone unchecked method to shared dyne bytes. Okay, and that's where you do that cheap clone. You do the, or I guess you shouldn't say it's a cheap clone. It's an atomic reference clone, which may or may not be cheaper or more expensive. I have no idea what the I don't know what the cost difference is, or at what point is an atomic operation less expensive than cloning certain amount of strings, right? Partial equals. Comparison is first done with the prefix. This check will fail for most strings, and the method will return immediately. As a result, many comparisons don't need to read the rest of the string beyond the prefix. By the way, I think this is so dang clever. This is so dang clever to store the prefix on the stack, and so you can just do such fast comparisons. It's mind-boggling how cool this is. Comparison between fixed-sized arrays are also very fast and well-optimized. Additionally, if both strings are short and inlined, we can compare the last 8 bytes without doing any pointer dereferencing. Pointer dereferencing might only happen inside the call to suffix when the strings are not aligned. There you go. It's super amazing, by the way. This is just such a super cool optimization, right? I just think I just absolutely blown away by this. What's the gain of this? It's being able to do German strings, showing that there is this optimization that actually is possible in Rust. It's just an exceptionally difficult possibility, right? If I jumped into C without a solid C and CPP foundation, I will miss a lot. It can be difficult. I don't have that solid of a CPP foundation. I had an okay foundation with C. I'm definitely not the world's best C programmer, and I immediately saw what's cool about Rust. It's pretty neat, but I wouldn't say that it's easy. Partial ordering. Ordering also takes similar execution paths to comparison. We immediately returned if the order can be determined just from the prefix. The string suffixes are only compared when the prefixes are equal. Pointer dereferences are also avoided by checking if both strings are inlined. There we go. So partial compare, we can do that. We can do the left-hand side, right-hand side. I assume if these, there we go, we can do they are equal, they are inlined, or we have to do the suffix comparison. Ah, super cool. Super, super cool. I think this stuff is super cool. I don't know. Like, you just do a comparison. With the prefixes. Wow, I love this optimization. I almost made the impossible. Let's see. I made the impossible possible. Implementing German string in Rust requires knowledge of Rust's memory model and type layout, but is relatively easy. So I want to be completely fair to Rust right now. What Rust is really good at, or what it's been designed to do, is to create a memory safe, something that should be or can be as fast as C, right? That was its kind of goal. It's a system level programming language in which you can determine the layout. But that stuff is exceptionally difficult to do. And so from his vantage point, the writer of this, it was very easy because of the already the predefined knowledge, like understanding what Phantom is, how to use Phantom properly, understanding this layout and how Rust actually does allocations under the hood, how to effectively just called malloc, right? I don't know how to call malloc, right? I have never done any of this stuff. And so you can make a safe version of something that is fairly difficult, which is very impressive. And so that means you can still have all the speed and all the good stuff. But for us, it looks absolutely bonkers because we just don't, most of us, at least in this chat, don't have the relative Rust expertise to understand this. And so I don't want to dunk on Rust because this stuff all looks like, some of these things just look a bit mind-boggling, right? Putting it all together, like this right here, it looks like a lot, right? And so I don't want to dunk on it because Rust is hard in this kind of sense, because this is a very edge case about Rust. Whereas where I think it's easy to dunk on Rust is simple performance optimization, right? Lifetimes. Yes, it is safe, but to be able to do lifetimes, you end up leaking onto structure, like structs and functions become colored, and they kind of spread throughout your system. Once you have one lifetime, it just keeps on doing that whole spreading thing. I think Ryan Winchester may still have the funny meme at the top of his profile. If he does, I hope he does. Yeah, you could do the exact same thing with a lifetime, which is instead of having async function, you just have function with a lifetime. And then once that happens, everything has to have this lifetime. I do, just for you. Thank you, Ryan. I literally go to this thing like once a month. I go there and show this off. You can never change that. You may never change that meme, Ryan. It's a great meme. Actually, you can if you want to. I mean, I feel like that's a much more fair thing to critique Rust, because the reality is you could write Rust for the next 5 years and probably never run into any of these things. Whereas you will run into this if you write Rust for the next year. Lifetimes need to be a rethought in Rust. Lifetimes can be exceptionally difficult. I love The problem with Rust is that it's a systems level programming language, so it has to be designed this way, whereas OCaml can get away with a lot of these things because it is garbage collected. So you can have lifetimes that are associated with a function as opposed to being associated with a data type. And I think that does a really good, it just makes it much more friendly, right? I don't think they need to be rethought. I think if you do that, you ruin the language. You could potentially ruin the language. Maybe there's an easier way forward, T-Nord. Maybe there's an easier way forward that you could do lifetimes without all the complications. I don't know if that's possible. I haven't thought about Rust that much to be able to say that's true or false, but nonetheless, because I know there's some whispering, I think from Graydon Hoare, the guy that originally invented Rust, saying that lifetimes could have been easier. So I'm not really sure if it can or can't be. Yeah, they're not insane. Lifetimes aren't crazy. They just can become huge pain in the asses, right? The moment you start trying to go from a clone system to get something out to a lifetime system to make it fast, it just requires a lot of effort. That's that. The name, and they still do not prevent memory leaks. Yes, memory leaks are just you can memory leak all you want in Rust. That's not what Rust is saying. You can. That's not what Rust's purpose is. Yeah, a lifetime as a concept is easy, but refactoring is hard. Agreed. Refactoring can become very tricky, and then it becomes progressively more tricky once you layer on async. If that makes sense. All right. Anyways, great article though. It was very cool to start off with this is an impossible type in Rust, and then showing that it actually is possible through the deep dark magics of unsafe and understanding how layout works. Super cool. I will say that's one cool part about Rust is that you could spend the next 5 years understanding it and becoming really good at the language. There is something that's very beautiful about that a language that allows expertise in, but it also is a two-edged sword because then you also have to work with people that are an expert in the language, and for you to potentially understand some of their code may require years of training, right? And so it's a two-edged sword, but it's super cool, right? If you've ever worked with a CPP wizard, which I was on a team of like 5 CPP wizards, I'm just saying, it can get really wild, right? It can get really, really wild where you're just like, dude, I don't understand what's happening here. That's one thing. That's one reason why I really have enjoyed my time with Zig, is because Zig is just so straightforward. It's literally just a straight line from what you do in your head to what you do in the computer. Oh, you need to create something on the heap? You must call malloc. Oh, you want it to be stack? Then you just create it. It's just so, it feels really nice to work with, honestly. I genuinely enjoyed my time with Zig because you don't need all of the advanced natures of Rust, and you can create relatively safe programs, safer than you would in, say, C when you need to. Anyways, the name. Well, I guess that was my name, technically. That's my name. You just heard my name. It's a very long name. It's in fact, I would say that name competes with some German words out there. Yeah, so German.